Hello everyone, welcome to Pre-Algebra with Miss Betsy. I'm glad that you've joined me today. What we're going to be discussing is the whole concept of scientific notation and the fact that this is a neat method that we have of expressing either very large or very small numbers. For my text today, I am using Pre-Algebra for Christian Schools. It's published by Bob Jones University Press, and I am using the first edition. If you're using the same text I am, I'm in section 7.7. It's entitled Scientific Notation, and I'm on page 236. You don't have to use the same text. If you're interested in scientific notation, this will give you a good, basic, quick overview of how that notation works. Before we get started, though, I've got, of course, a couple of lame jokes for you. First off, why do dragons sleep all day? Well, it's because they like to hunt knights. And the next one for today, why are elephants poor? They're the only ones that work for peanuts. So let's go ahead and dive right into this whole concept of scientific notation and see what we can come up with. First off, what I've gone ahead and written three statements here on the board, and let's go ahead and look at this and review shortcut methods that you've learned in the past for multiplying by a power of 10. And you'll remember that powers are when we use exponential notations here. Exponential notation that indicates to us how many times this bottom number here, which is called the base, is used as a factor. Here we have a base of 10 that's used as a factor one time. So we're going to multiply by 10. Over here, when we have 10 to the second, our exponent of 2 indicates that 10 is used as a factor twice, or 10 times 10, which is a value of 100. Our final example here, where we have 10 to the third, our exponent of 3 indicates that 10 is being used as a factor 3 times, 10 times 10 times 10, which gives us a factor of 1,000 that we're multiplying. So I have 5.2 times 10 to the first, 5.2 times 10 to the second, 5.2 times 10 to the third. Now, let me digress just a moment here. I've really talked to my pre-algebra kids and said, let's lose the x for multiplication, because when we're working with algebra, you have x used as an unknown variable so frequently, there's no reason to be using that x. We use sometimes not even a raised dot, but we just use parentheses. However, this is the form that scientific notation takes. A number between 1 and 10 multiplied by a power of 10. So this is one case where we do want to use the x to indicate multiplication. Okay, so back to what we have here, 5.2 times 10. If we multiply 5.2 times 10, we get 52. 5.2 times 10 squared, I showed you that that's 5.2 times 100, which gives us a value of 520. Our final example, 5.2 times 10 cubed, is 5.2 times 1,000, or 5,200. So, what relationship can we see here? Remember, when we multiply by 10, we move our decimal point 1 unit to the right, don't we? Our decimal point was here, we multiply by 10. There's the new location of our decimal point. We multiply by 100. We have 5.2. Multiply the decimal, move the decimal place 2 units. And the location, new location for our decimal is at the end of 520. 5.2 times 1,000. We're moving our decimal point 1, 2, 3 units to the left is what we've done, because it's true. 5.2 is 52 times 10. 5.2 times 100 is 520. 5.2 times 1,000, 5,200. So what we're actually seeing here because we know that when you multiply by 10 or 100 or 1,000, 10,000, that you're going to move that decimal point to the right the same number of zeros that we have. And that's what you learned when you were back in elementary school. And what you're seeing here, how many places did we move the decimal when we multiply by 10? 1. When we multiply by 100, we move it 2 places. When we multiply by 1,000, we move our decimal point 3 places. So what you have in scientific notation, when you're multiplying by a power of 10, that exponent right there indicates to you exactly the number of decimal places that your decimal point is going to move to the right. So if I had 5, 6, 7, 8, 5.678 times 10 to the 5th. And actually, you know, I teach higher level things as well. So let's get rid of that 5.678. Let's just go 5.6 because I don't want to do that one right now. What does this indicate to us? We're going to move our decimal point 5 units to the right. So if I have 5.6, I'm going to move, let's just go ahead and sketch in some extra zeros here, because we know that when we're multiplying by 10, our number gets bigger. 52, 520, 5,200. So we know there are going to be some extra zeros that have to be tacked on to the end of 5.6 in order to be able to move that decimal point 5 units to the right. So let's see where we get. 1, 2, 3, 4, 5. That right there is the location of our new decimal point. 5, 6, 1, 2, 3, 4. 5.6 times 10 to the 5th gives us a resulting product of 560,000. And all we've done is we've moved our decimal point 5 units to the right. So that's what this exponent is going to indicate. When you have scientific notation, that exponent, when it's positive, tells you how many units you move the decimal point to the right. Okay, well let's say that we have a whole number. Just going to go a straight whole number now. How are we going to express that using scientific notation? It's really very straightforward. I'm actually going to go ahead and take this 5,200 and I'm going to work backward for you and illustrate how we ended up with 5.2 times 10 to the 3rd. Okay, what's the very first thing you do when you're writing a number in scientific notation? We have to locate, or relocate if you will, your decimal point so that it is between the first 2 non-zero digits. So if we have 0, 0, that doesn't work. The first digit has to be greater than 0. Okay? So we've now relocated our decimal point. And what we're going to do now is we're going to multiply by the power of 10. That shows us how many places we have to move this decimal to the right to get back to the number that we wanted to be defining or describing using scientific notation. So if we wanted to be writing the number of 5,200, when we moved our decimal point to get it between the first 2 non-zero digits, how many places are we going to have to move that decimal point to the right to get back to our original problem? 1, 2, 3. So what we're going to multiply by is this same power of 10. It's 10 to the 3rd power. The exponent, or the power, is exactly related to how many places that decimal point has to move to the right. So what we would have for the scientific notation then would be 5.2, because we relocated our decimal point. We moved it so that it was between the first two non-zero digits. 5.2 times 10 to the third. Because we started with this number, we moved our decimal point so that it's between the 5 and the 2. To get back to our original number of 5,200, what do? We have to move that decimal point 1, 2, 3. So 5.2 times 10 to the third is how we would represent 5,200 using scientific notation. So what is your decimal point showing? What is our exponent showing? Our exponent is showing us how many places we're going to move our decimal point when we multiply. Now, if you have a positive exponent, the decimal point moves to the right. If you have a negative exponent, the decimal point moves to the left. This is key factor here, kids. Positive exponent, move the decimal point to the right. And what do you think we're going to need to do if we have a negative exponent? Yep. That's exactly what you have to do. If you move to the right for positive, you move to the left with a negative. So we're going to move the decimal left. Decimal point left. So let's think about what happens as we move further to the left. That decimal point further to the left, the number's getting smaller, isn't it? As it moves further to the right, the number's getting bigger. You see this here. 52 times 10 is 520, times 10 is 5,200. So the larger the positive number, the larger the positive exponent, the larger the number. Similarly, the smaller the number, you might think of it as being like maybe a larger negative, like a -7 is a larger negative than a -1, or a -100 is a larger negative. It's actually a smaller number, but the bigger the number gets when it has been made negative, which I'm sorry for those of you who are watching me and just not happy with the technical correctness there, but it still illustrates the same point. If the number gets, the further you get to the left on a number line, this when we're indicating the exponent, when we're using scientific notation, the smaller the number is going to be. So this picture will perhaps help someone. Here we have 0, 1, 10. Okay. It's not to scale. The further you get out here for exponents, the much larger your number becomes, because we're multiplying by what we call a factor of 10. Similarly, the more you go in the negative direction on your number line, the much smaller your number becomes. So yes, obviously -1,000 is smaller than a -1. But sometimes, as people are learning how to work with negative exponents, if you think of that as being a bigger negative, it will help you understand what's going on. Okay? So let's go ahead and do some problems and see what we come up with. Okay, scientific notation. What is the format for scientific notation? Well, it has two parts. It has a number between 1 and 10, and we're multiplying that by a power of 10. The exponent in the power of 10 tells us how many places we move the decimal point to the right or to the left. If it's a positive exponent, we're going to move the decimal point 3 units to the left. So we have a positive exponent. What does that mean that we should do? We're going to move the decimal point to the right. Move the decimal, how many units to the right? Move, or how many places to the right? Move the decimal point 3 units to the right. How do I know 3 places to the right? I'm sorry, I keep saying units. Move the decimal point 3 places to the right. Here's our first problem, 4.7 times 10 to the third. This is the format that scientific notation takes. You have a decimal number between 1 and 10 multiplied by a power of 10. We want to take this number that's in scientific notation, convert it into standard notation. What do? We look and see, is the exponent positive or negative? The exponent is positive. What does that tell us to do? It tells us to move the decimal point to the right. How many places? 3 places to the right, because the exponent tells us how many places we're going to move that decimal point. So, 4.7, let me just tack on some extra zeros. You're going to have to add zeros to the end of the number when you're multiplying by a positive power of 10. And we want to go ahead and move our decimal point 3 places to the right. 1, 2, 3. So that's going to be the new location of my decimal point. So what has happened when we multiplied by 10 to the third? We end up with 4,700 as our result. Everybody see that one? Now, what are we going to do when we have a negative exponent? How about if we have 2.36 times 10 to the negative 4. Okay. You say, oh man, Miss Betsy, we got a problem here because we have 2 numbers after the decimal point. That's fine, and you're going to frequently have multiple digits after the decimal point, because the way that you do scientific notation is you simply locate your decimal point between the first 2 non-zero digits. So, particularly in science, you might have multiple decimal places depending on the precision with which your precision and accuracy that you're indicating with your measurements. So, what's the first thing that we do? We look at the exponent. Is it positive or is it negative? So we have a negative exponent. And what do our exponents indicate? They tell us how we're going to move the decimal point. They tell us how far we're going to move it. They tell us in which direction we will move the decimal point. We're going to move the decimal point how many places? 4 places. Are we going to move it 4 places to the right or 4 places to the left? We're going to move 4 places to the left because we're multiplying by a negative number. Let me make this one blue also, except I don't want it to say left again. 4 places to the right. So, what is this telling us to do now? We're multiplying by a negative number. We're going to move units to the left. 2.36. Because we're moving our decimal point to the left, we're going to add zeros in front of the 2.36 so that we can move our decimal point as many places as necessary. We start here. 2.36, we're moving 1, 2, 3, 4 units to the left. 4 spaces to the left, 4 decimal places to the left, okay? This becomes the new location of our decimal point. So, if we have written in scientific notation 2.36 times 10 to the minus 4, that actually has a value of 0.00026. And you can see, grasp immediately why scientific notation can be so valuable, because it's very easy to get lost in all of the zeros when you have very, very small numbers. Now you notice that I put the decimal point here so that I had a leading zero. We want to do that when we have decimal numbers because that sort of screams at you. If you begin a number with a 0, that's saying, hey guys, this is a really small number. Make sure that you don't think of this as a big number, I guess. That's really all that there is to scientific notation, is realizing that it's composed of 2 parts. First, you have a decimal portion that is a number between 1 and 10. Then you're multiplying that by a power of 10. The power is either going to be positive or negative. If you have a positive exponent, that means that you move your decimal point the same number of places to the right as that exponent is. We have an exponent of 3, it's positive, so we're going to move our decimal point 3 places to the right. Now, we have 2.36 times 10 to the negative 4th. We look at that exponent, it's negative. Because it's negative, we know that we're going to move our exponent to the left. How many units here will we move? Well, we move the same number of places to the left as that exponent is. So we're going to move our decimal point 4 places to the left. That's basically all that we have going on with scientific notation. Now let me show you something else this shows you how to move back and forth from standard notation to scientific notation, from scientific notation back to standard notation. But what are we going to do when we multiply numbers that are involved in scientific notation, that are written using scientific notation? Let me go ahead and show you an example from your book. This is problem number 21. We're on page 238. Page 238. Once again, though, you do not have to have this text because you can follow right along with me. 2 times 10 squared. What in the world are we going to do here? Well, this looks perhaps a little bit confusing to you, but all we have is 4 factors here. We have 3 times 10 to the 4th times 2 times 10 squared. And you remember that multiplication is commutative. It doesn't matter the order in which you multiply factors together. So what is really nice is that you can regroup. We can regroup our decimal numbers together. That was intended to be written as a 3. 3 times 2. And we can group our powers of 10 together. Okay? Now you might be thinking, you called this a decimal number. These aren't decimal numbers. Yeah, it's a decimal number. Whole numbers are decimal numbers because you can write them 3.0 times 2.0. All we did was change the order in which we're going to multiply these four factors. What's 3 times 2? What's 6 times, what's 10 to the 4th times 10 squared? That's 10 to the 6th. Remember, when you multiply exponentials that have the same base, you keep the base and you add the exponents. Go ahead and rewrite this in scientific notation form. 6 times 10 to the 6th. Okay? Pretty straightforward as soon as you grasp the concept that we simply have four factors here. And we're going to move them around so that we end up with some convenient multiplication. Let me do another one for you. Four times 10 cubed, or 4 times 10 to the 3rd, times 2 times 10 to the 4th. We're going to regroup, move our factors around. We have 2 times 4, 10 cubed times 10 to the 4th, 8 times 10 to the 7th. So I didn't even need to write any more steps than that. 2 times 4 is 8. We're going to have this written in scientific notation form, times 10 to the 7th. Okay? That's really pretty much all that there is to scientific notation. Let me do one more that's a little bit more involved example. Just for those of you who are really grasping the little bit more difficult problems at the end of each section. Actually, let me go ahead and do 2. We have 1.4 times 10 to the minus 5 times 5 times 10 cubed. Okay, don't be afraid of this with the negative exponents. Just going to regroup our non-powers of 10 together, times 5 times 10 to the negative 5 times 10 cubed. Okay, what is 1.4 times 5? That's 7.0 times 10 to the negative 5 plus 3. Remember, when you multiply exponentials together with the same base, you add the exponents. So 7.0 times 10 to the negative 2. And that's all you need to do. That is your answer. 7.0 I'll take here. I would also accept 7 times 10 to the minus 2. Okay? Let me show you one more quick example. This is problem 27 from section 7.7. 14.3 times 10 to the 4th. Okay, we know what we do to make this into standard notation. We're going to take our decimal point. We're going to move it 4 units to the right because we're multiplying by a positive power of 10. However, that's not what our instructions tell us to do for this problem. Our instructions say, write this number in scientific notation. And you say, Miss Betsy, it's already in scientific notation. Well, no, it's not. because the 14.3 is not acceptable. What do we need for scientific notation? This number has to be between 1 and 10. Okay? Which is a problem for us because 14.3 is not between 1 and 10. However, it's not hard. We just convert this number into scientific notation first. How do we do that? We relocate our decimal place so that it's between the first two non-zero digits. Okay? 1.43. What power of 10 do we have to multiply by? How many units how many places do we have to move that decimal point to get back to our original number? One place. To the right or to the left? We're moving that one place to the right. So we simply come up with 1.43 times 10. I wrote 10 to the first in there, so it just screams at you that we have a power, 10 to the first power. We move our decimal point one place to the right. Now we have 1.43 times 10 times 10 to the fourth. 1.43 times 10 to the first times 10 to the fourth. I'm adding extra steps in here to make it crystal clear what we're doing. 1.43 times 10 to the 1 plus 4. We have the same base, we're adding exponents. In scientific notation, it's 1.43 times 10 to the fifth. So go ahead and play around with this scientific notation, enjoy it, learn it, because you will see it again. You will see it again in Algebra 1, in Algebra 2, you'll see it in chemistry, physics, biology, any science thing. You're going to be using scientific notation. So I'll see you next time.